Next, we'll have a team from the University of Florida. Oye, qué bolá, presenting a realistic approach to utilizing Cuba's current telecommunications infrastructure to provide readily available communications accessibility to the population.
All right. Hello, everyone. Thank you for attending our presentation today. We are Team Oye que bolá. The topic of the project we'll be presenting is a realistic approach to utilizing Cuba's current telecommunications infrastructure to provide a readily available communications accessibility to the population. My name is Eric Bolnes. I'm from Margate, Florida. I'm a senior studying mechanical engineering.
My name is Antonio Diaz. I'm also a senior studying mechanical and aerospace engineering at the University of Florida. I'm from Miami.
And my name is Fernando Villafuerte. I'm from Arcadia, Florida, and I'm a senior mechanical engineer at the University of Florida as well.
And with that, we'll go into the agenda for our presentation today. First, we'll go over an overview of the current state of telecommunications in Cuba. Then we'll present our engineering objectives to meet the infrastructure deficiency that Cuba has in telecom. After that, we'll present our system design on how we plan to meet those engineering objectives. Finally, we'll go over a system financial analysis for the system that we've engineered, our engineered solution. And finally, we'll present the future outcomes if our engineered solution were to be implemented correctly and effectively. So with that, we'll go into a chart here which shows Cuba relative to many other countries in the world in terms of internet usage. On the x-axis, we have freedom on the internet, which is composed of multiple criteria, which determines freedom when using the internet, and the y-axis shows the percentage of the population able to access the internet. Now in Cuba, approximately 5% of the population is able to access the internet. This is restricted mostly to government officials and writers. However, some academics, doctors, and engineers also have access to some form of the internet. More so, 25% of the population has access to the intranet, which is a local network within the island amongst which they can send emails to each other. So as you obviously can see, Cuba is severely behind the rest of the world. And here's another graphical representation showing some major websites as bubbles. Now, the size of the bubble is representative of how many people access a particular website. So the blue bubbles are some major United States websites like YouTube, Google, Facebook. And then we'll zoom in here to the website blogspot.com. Now just outside this website are some small purple bubbles. These are representative of the major websites accessed in Cuba. So as you can see, Cuba has a very relatively small internet presence relative to the United States. However, Cuba does have one link to the World Wide Web, and that is the ALBA 1 cable. It's a submerged cable which was initially, it was a $70 million project initiated in 2011. However, it did not go live until 2013. The cable is completely submerged and goes from Venezuela, and it links to Jamaica and Cuba. In addition to this submerged ALBA 1 cable, there also exists a fiber optic backbone which spans the length of the island. The fiber optic backbone branches out to various major cities throughout the island. Now, although these fundamental telecommunication infrastructures exist, there's still a major accessibility problem in Cuba. As you can see in this picture, there's people waiting to attend what's known as a cyber cafe. There are 150 cyber cafes spread throughout Cuba. In order to use a cyber cafe, you must provide identification and then pay approximately $5 per hour to use a machine. To put $5 per hour into perspective, the average Cuban makes about $20 per month. So they're paying nearly a quarter of a month's salary to go online, either use the internet or intranet for an hour. However, while they're using the machines, they're being closely monitored, not only physically, but also all their emails are being read, and all the websites they go on are being monitored. And if anyone is deemed to be violating the correct protocol, they can be severely punished. And here's another photograph of a typical cyber cafe. You can see the front desk here where users are required to go log in, provide identification, and pay for the service. So ultimately, the Cuban population is left in shackles when it comes to communication transfer. So ultimately, there's a great need and push for advancement. There's been multiple attempts to establish illegal Wi-Fi networks. Many times these networks are taken down and then reestablished in a different location, mainly by the same people. In addition to the illegal Wi-Fi networks, there's also been an increased presence in smartphones throughout the island. Many people have received smartphones from their family and can download apps through machines that store the information for the apps. And there's also been opening of shops that can repair smartphones because it's been becoming so popular. And there's also a Connect Cuba movement that's going on at the international and national level. And various signs of graffiti can be seen throughout the island, sponsoring the increase in the push for spreading telecommunications throughout Cuba. So we wanted to design and engineer a system that can meet these needs. The main criteria for our system was we wanted it to be readily accessible, such that anyone can access it without the severe struggle that they go through at the internet cyber cafes. Secondly, we wanted it to be sustainable, such that it could be implemented and installed and used for long periods of time. Third, we wanted it to be durable, such that it could withstand natural forces, such as hurricanes. And next, we wanted it to be enabling, meaning that it could provide modes for multiple methods of communication transfer. And finally, we wanted it to be cost-effective, such that it could be realistically implemented and used. And with that, I'll go over to Fernando to talk about the fundamental of our engineered solution.
So our solution for for Cuba's communication internet problem was a two-step implementation. One would be to use a network of self-healing fiber optic rings in major metropolitan areas so that, I apologize for that. So that we could ensure that the internet connectivity within the area would be sustainable. What these self-healing rings do is that if one of the transmitters for the internet around the city is brought down, it's able to heal itself and provide internet to the other transmitters. And then the second step would be a point-to-multi-point networking design scheme in which we would take the internet from, let's say, some of these self-healing rings and install it in an internet cafe. We would put a router together, and with the use of the router, we would have internet connectivity to people that were inside the internet cafe. This router would then be wired through an Ethernet cable to an access point or a device that transfers data wirelessly from a cable to there. And one of the advantages of that is that any of these access points that would be mounted on the building would be able to provide internet access to any of the residents in the surrounding areas, let's say the streets that were just walking by on their mobile devices or tablets. Through there, we would use point-to-multipoint networking in which we would provide data transfer to other adjacent buildings through these access points. And then these adjacent access points would also be connected to routers inside other buildings in which, by the use of Wi-Fi boosters, we could expand our network capabilities. So this is the model we came up for our access point. This is one of them mounted on a building. We took into consideration a couple of factors when we were designing it, one being Cuba's unreliable power supply. So we put a solar panel and a battery pack on our access point, and the other one was just external factors. So for all the devices that we picked in this case, we made sure they were able to be waterproofed so they could sustain that. This next animation shows just how easy it is to build one of these access points. The biggest note to take into consideration is how the access point in the center is able to rotate on the pole and then move up and down. And this is this advantage is for fine tuning. So in case we need to adjust the height of the access point to more effectively transfer data between one another, we're able to do that with this. And now I will transfer it over to Tony.
All right, so now that Fernando went over our general design for each access point, we need to determine where would be the best implementation for our pilot program. And as we can see in this on this map, Habana has a lot of tourism with 1.5 million tourist days as of 2010. And in Habana, which is divided into 15 municipalities, the municipality of Habana Vieja has a high population density of 100,000 for 4 kilometers squared. And because of that high population density, a wireless solution would have a huge impact. The first step of our analysis was considering a topography for using point-to-point networking, as Fernando was explaining, having a relatively flat landmass and a clear skyline benefits the system. And as we can see in this map in purple, it's 20 meters above sea level. And there's a slight elevation to the west, but it's relatively flat overall. Here are the locations we were considering. In purple are some hotels. In green are internet cafes and youth computing clubs. These are existing connection locations that we are confident we can build off of for our wireless design. Our first step in our signal strength analysis was using software for networking, and we made two big assumptions. One of them was that each block could be modeled as each block of buildings can be modeled as one unit, and that we would model it as concrete walls for structures. And in this first step, we have in green our access points and the signal dispersion. This video shows how we implemented and used that software. We're doing a demonstration here of how the areas of foliage are covered in drywall, which is 3 decibels of signal absorption. And in blue is, we're going to surround this fort because it's mostly concrete, and concrete is these blue walls which absorb 12 decibels of signal. Our final results are, as you can see in this map, 12 different access points. 20 different access points, sorry, with 8 different channels. And we dispersed the channels, similar channels, as far apart as we could to avoid signal noise and interference from the same access point channels. And it's blown up on our poster as well. Our data rates on the image of mostly blue, that's about 390 megabytes per second for the majority of the island, and not for the majority of the area. And our signal strength is the other image as well. And as Fernando was mentioning, we took into consideration strongly our risk and mitigation analysis. He covered water damage and a few other risks and mitigations, but there's also to take into consideration damage to ALBA 1, which is the single point of access to the international connection that Cuba has. And it's highly unlikely, but if damage does occur, it would be severe. And in that sense, it could come from ships dropping their anchors, storms, or even wildlife. And as we can see here, this shark finds this fiber optic cable pretty tasty, and se está comiendo tremendo cable. And now to Eric for some financial analysis.
We performed a financial analysis on each individual unit. The unit shown on the right would cost approximately $2,100 to assemble. That includes the cost for a solar panel, the access point, the battery, and all the mounting hardware. In addition, we wanted to analyze how much it would cost to sustain the 20 access point system over a 3-year period. So we took into account all the personnel, training, implementation, replacement hardware costs, and came up with about $65,000 for a 3-year period for 20 of the systems shown on the previous slide. So we wanted to take this pilot program and extrapolate it to cover about 115 densely populated regions throughout the island. So what we came up with was that it would cost approximately $11.1 million to provide actively, readily available Wi-Fi to 1.2 million people. As you can see on the map, these are some of the densely populated regions in which the system would be implemented. So to put the cost into perspective, Atexa, the major telecommunications company in Cuba, spent approximately $5.6 million per year from 2003 to 2008 on telecom expansion projects. So to cover a cost like this would take only about 2 years at that same spending rate. And now we'll go back to Tony.
So what's in store in the future for Cuba with a system like this? Currently, as Eric mentioned, we are at about 5% internet penetration rate as of 2014. Our system would increase it to about 10% more, which would take it to 15% by 2017. And this trend is based off of a similar trend seen in the Dominican Republic in blue. And It could continue to be sustained by expanding with Wi-Fi boosters to the interior of buildings and to rural areas with other Wi-Fi technologies. What does a tourist see currently if they were to visit Cuba? They would see that there's a lack of communications to the island from abroad, so they won't be able to stay in touch with their family. And they would also see that there's a lot of advertising on offline apps that would work without maps, without internet connection or GPS. And that's very discouraging for a tourist to see. This is something we would hope to change by implementing a wide-scale wireless application. It would also impact education. There's a lot of free tools online that would help the general public. And not only that, a big part of Cuba is also medical advancements. And this is just one example of a smartphone adapter that was made to perform retinal scanning. And wireless technology would help educate the current staff, and it would provide improvements. And just as you can see, 500 USD, including buying a new smartphone, compared to a traditional bulky equipment that would cost 16,000 USD. And the images are of similar quality. And there's plenty more examples similar to this that will be enabled with future technology expansions. And we'd like to acknowledge all our mentors. We wouldn't really understand what we were doing without them. And that's all for questions.